Oh, there we go. I will begin with a word of prayer. So, Dear Father, we thank you for the weekend and time to relax and refresh and waste our time. May use our time profitably, I hope, anyway. But just pray to be with us today. Help us to, again, Lord, glorify you what we do. Just pray, Lord, that we just wrap up our thinking about cyclic groups today, Lord. In your name I pray. Amen. Okay, so we're a good way into lecture 6. We're now working on theorem 1.6.15 in my notes. And here's the theorem. If G is a group, right, with A in G, and the order of A is equal to n, and k is a positive integer, then, sorry, this marker's kind of sad. The subgroup generated by a to the power k is equal to the same as the subgroup generated by a to the greatest common divisor of n and k. And the order of a to the k is simply given by the order of a divided by the greatest common divisor of n and k. Excuse me. So let's look at the proof of this. All right, so I'm going to let D equal the greatest common divisor of n and k, all right? And I'm going to observe, what's that mean? Among other things, that means that k is equal to zd for some z in the integers, right? I mean, I guess you can safely say it's a natural number, right? If we're assuming k is a positive divisor and d is the greatest common divisor, I could say z is a natural number without without fussing here. All right. Excuse me. So let's suppose that x is an element of the subgroup generated by k. So what I'm doing right now is I'm picking an x from this set, right? My goal is to show that x is in fact also in that set, which will show that this is a subset of that. All right, and then we're going to show that this is a subset of that. Once we have double containment, that will show that the sets are equal. Okay, so what's this mean? This means that x is equal to a to the k to the power y, right? For some y in the integers. That's the definition of this, right? And then thus we have x is equal to a to the k times y. Let's see here. But what's that equal to? That's equal to a to the zd times y, right? But of course that's a to the d to the zy power, right? By laws of exponents. In our current notation, this is that, right? So this is an element, of course, of a to the GCD n comma k. Thus, we have that the cyclic subgroup generated by a to the power k is a subset of the cyclic subgroup generated by a to the greatest common divisor of nk. So, next step, we will pick a point on the other side. I'll do it in red. Suppose we have, stick with the notation of my notes, W. I use different letters to make sure there's no confusion here. W, an element of a to the GCD of n comma k, right? Hence, W is equal to a to the d to the u power for some u in the integers. That's what it means for w to be in this cyclic subgroup. All right. Now we can apply Bezout's identity by Bezout. We have p and q in the integers such that what? P times n plus q times k equals to d, right? Remember, d is the greatest common divisor of nk, if you forgot. So we can reach the greatest common divisor by an integer linear combination of n and k, in this case coefficients p and q, and then it's just a straight calculation. So w is equal to a to the d to the u, right? But that is equal to a to the, here, let me just, nothing terribly clever here, I don't need my notes. So this is a to the pn plus qk, that's d, right? All of that to the u power, excuse me. And so what's that? That's equal to a to the n to the pu times a to the, let's see here, what am I trying to show? I'm trying to show that this is a subset of that, right? So I'm trying to rewrite this as a to the k to some power. So this is a to the k to the qu, using the laws of exponents there, right? Now, I suppose if I wanted to be all picky and pedantic here, I could spend 20 minutes unraveling that step by glorious step and make you do the same. But I'd rather have you do algebra and say laws of exponents with understanding. But there is, of course, like 4 or 5 steps, folded into that equality right there. Right. All right. What's a to the n? Yeah, by assumption that's e. I should say at the start of this, suppose order of a is equal to n, right? So this is e. And so what do we have? We have that w is equal to, now e to the pu is what? The identity to any power is the identity again, right? So this is a to the k to the qu. So that's an element of what? That's an element of this guy, right? So now we've shown that a to the GCD of nk is a subset of a to the k. Therefore, they're equal. Now, I'd say the proof is done, but it's not quite done yet, right? That's the first part of it. What else do we have to show? See, we're still supposed to show that the order of a to the k is this, right? How are we going to do that? Well, we have, on the one hand, that a to the d, right, raised to the n over d. Now, how do I know that n over d is an integer? Right, exactly. because d is a divisor of n. Now, a to the excuse me, a to the n is equal to e, right? So what's this show? We have that the order of a to the d is less than or equal to n over d. Now, if 0 is less than I is less than n over d, then we have, of course, that di is less than n. So what's that say about a to the di? In other words, a to the d to the I power. That's not equal to what? If the order of a is n, right, and di is a number less than n, a to the di is not equal to e, by definition of order, n, right? So what's that show? Therefore, the order of a to the d is equal to n over d. Right? What else do we know? We know that the order of an element is the same as the order of the subgroup that it generates, right? So this is also equal to the order of this, not that yet, right? What do I have to do to make this equation make sense? We proved last class that the order of an element is equal to the order of the subgroup it generates, right? So this needs that. Now we're good. But what else do we know? We also know that the order of a to the k is equal to the order of the subgroup it generates, right? However, what else have we shown at this point? We have shown that these two subgroups are, in fact, one and the same. If they're the same set, they have the same number of elements, right? So therefore, the order of a to the d, which is equal to n over d, is also equal to the order of a to the k, which is to say what? The order of a to the k is equal to n divided by GCD of n comma k. There you go. That is the proof of theorem 1.6.15 in all of its glorious detail. Any questions about this before I meander on? So there's a corollary from this, a flower. Let's see here. And this one you're going to like. This one's super, super useful. So corollary 1.6.16 states the following. If the order of a, I can't write a, if the order of a is equal to n, then the cyclic subgroup generated by a to the power I is equal to the cyclic subgroup generated by a to the power j, if and only if the greatest common divisor of n and I is equal to the greatest common divisor of n and j. All right, so this is a corollary, so its proof should be fairly easy. Let's see how it goes. So let's see here. Let's start out by assuming what? I mean, obviously we're going to suppose the order of a is equal to n, right? And this is if and only if, so I could write it this way, right? Let's consider this direction, right? Let a to the I equal to a to the j, right? So what can we do? So that gives us that the order of a to the I is equal to n over the greatest common divisor of n and I, right? And it also gives us that the order of a to the j is equal to n over the GCD of n comma j, right? by the theorem we just proved, the latter part of it. So what can you get from that? And of course, this immediately implies what? We proved that last time, right? I mean, set theory, first of all, says the number of elements in both are the same, right? But then we proved that the order of the subgroup is the order of the element last class, so therefore the order of the elements must also be equal. But the order of the elements is also n divided by GCD. And so then, thus, n over GCD ni equal to n over GCD. And you can, I think, do the algebra here, right? The GCDs are equal, right? How about the other direction? We have what? So assume that the greatest common divisor of ni is equal to the greatest common divisor of nj. That tells me what? It tells me that the order of a to the I is equal to the order of a to the j as, you know, n over GCDI is equal to n over GCD nj in the theorem. So then what? Oh, I'm sorry, I seem to have wandered. Let's see here. So, trying to show that the cyclic subgroup generated by AI is equal to by AJ. What do we have over here? Oh. I'm sorry. I'm working too hard here. This line is unnecessary, right? Let's just skip that. I need to use the first part of the theorem, right? It's just duh. So we have, check it out. So like the subgroup generated by AI is equal to the subgroup generated by GCD, Ni, right? But that's equal to, by our assumption, a to the GCD nj. Then by the theorem again, this is a to the j, right? Duh. I'm making it more complicated than it needs to be. Sorry about that. So just using the first part of the theorem that links the subgroup generated by a to the k to the subgroup generated by the greatest common divisor of n and k, where k is equal to I and j here respectively. So there's your corollary. This flower was slightly harder to pick than some of the other ones we've done, but it's really not that bad. Really not that bad. All right. At this point, I'm about to show you a bunch of examples, so I think it would be smart for me to use the projector. So let me get that out. I'll wait a second here and let you guys, if you're writing. I was worried I didn't bring my laser. I got it though. Phew. Let's see here. Come on. Hello? Oh, okay, here we go. So this is the end of where we just got to. So there's a couple corollaries that come from this corollary. I can't say corollary. First of all, if G is a cyclic group of order n, then G is generated by a to the k if and only if what? The greatest common divisor of n and k is 1. Where does this come from? Well, G is generated by a, right? So that's a to the 1. So what's it take for the GCD of 1 and we need this is equal to this if and only if the greatest common divisor of n and k is equal to the greatest common divisor of n and 1. What's the greatest common divisor of n and 1? 1 is a divisor of which numbers? Except for 0. But yes. We guys got against 0. So mean. I'll let it slide. Let's see here. Anyway, so yes, GCD of n1 is 1. And so we need the greatest common divisor of n and k is 1. So there you have it. Now check it out. We've just proved that all of the generators, if you look at Z whatever, Z10, the generators for Z10 are found in the group of units, the set of numbers which are relatively prime to 10. So here's a more specific, this is really just a sub-case of that one. If k is in Zn, then k is a generator only if the greatest common divisor n and k is 1. It's just this corollary again. All right, so let's look at some examples. While this theorem we've stated for cyclic groups, it has application to non-cyclic groups. Because even in non-cyclic groups, there are cyclic subgroups, all right? So, for example, the dihedral group of order 2n, it's got a subgroup of rotations, all right? And the subgroup of rotations is actually a cyclic group generated by the fundamental rotation r, right? But you know what? It's also generated by r to the k, where k is relatively prime to n. That's what the corollary above says. So for example, if you're looking at the D16, what's a 16-sided regular polygon? I guess it's a 16-sided regular polygon, right? So if you're Gauss and you were a couple of years younger than you guys are right now, you figured out how to construct a 17-sided one using a straight edge and compass and stuff, right? And it's always kind of depressing if you look at what famous mathematicians did when they're 19. For the most part, it's kind of sobering, and it's like, yeah. But at least I get to understand what they did, so that's good. Although Maxwell gives us hope. I think Maxwell did some of his deeper stuff later in life. Anyway, I digress. So for R16, for D16, you've got r cubed, r to the 5th, r to the 7th, r to the 9th, r to the 13th, r to the 13th, r to the 15th. All of these guys, generators, right? And in some sense, it really just is a question of how you label the rotations, right? Which one serves as the r. In some sense, it is geometrically you can understand this result as these are different possible ways of sort of relabeling the rotations. But anyway, more on that later. Galian gives a killer example on page 78 with the U20. I'll look at U14. U14, 1, 3, 5, 9, 11, 13, all right? So, in fact, U14 is cyclic. It's generated by 3. You can easily calculate that. 1, 3, 3 squared, 3 cubed, 3 to the 4th. 1 goes to 1, 3 goes to 3, 9 is 9, 27 is 13. And then 13 times 3 is 39. 39 less 28 is 11. And then 11 times 3 is 33, less 28 is 5. That's how I think of it anyway. But anyway, as you can see, that's the whole shebang. So U14 is cyclic, and the order of U14 is 6. But you notice then, only 1 in 5 are relatively prime to 6, right? So that means besides 3, the only thing else which is a generator for U14 is 3 to the 5th. So 3 to the 5th is 5. So either 3 or 5 serve as generators for U14. That's how this works. I think it's best for me to project these examples, because if I write them out by hand, I'm going to make a stupid error. Then you guys can be like trying to copy it down. It's just dumb. It's better to talk amongst ourselves about these numbers. So let's talk. All right, some more talk. Oh, look, work. Now I will tell you the source of my my nefarious problems. Actually, they're not so nefarious. These are crafted by my brother Bill. These are Bill's problems. Bill has taught abstract algebra like, I don't know, a dozen times. So these problems come to you from a wealth of experience. Bill's way of teaching, of making homework problems also, he does not delight in busy work. He wants to give you problems that force you to chase down your misunderstanding. Right? So after you work these problems, you will learn something. And they should leave you understanding what cyclic groups are. Which is not to say that these will be easy. But they will be easier if you actually use the theorems in Lecture 7. So those theorems, those problems in Lecture 6, you are allowed to use Lecture 7 technology for, okay? Just to be clear. That's not always the case, but it's certainly the case this time. I'm telling you right now. Here we are. All right. So, a to the fifth. So the next lecture, I just start out with 4 examples just to get us in the way of thinking. All right. So, first of all, there's basically 2 kinds of cyclic groups we look at. There's either like the power notation, a to the power n stuff, right? Or there's Zn. These are our 2 main go-to examples of cyclic groups at the moment. So if you have a to the power 5, you have a trivial subgroup, right? What are the other possible subgroups? That's what we're going to look at in this lecture, is what are possible subgroups of a cyclic group. So if you look at A, well, that generates the whole thing. What's A squared generate? It also generates the whole thing. A cubed. Oh, I think I'm missing. Yeah. What idiot wrote these notes? Let's see here. Squared, fifth. Oh, I should go to the third next here, right? Like if I multiply by a squared times a, I get a cubed, right? And then multiply by a squared again, I get back to the start. So yeah. I got back on the straight and narrow here again, right? This time I can add. You go to the third, then 3 plus 3 is 6, which is 1. 1 plus 3 is 4. And then 4 plus 3 is 7, which is 2 mod 5. Well, that's kind of the thing, right? A multiplicative group, order n, has exponents which work in terms of modular n addition, right? So there's this like natural correspondence between Zn and the multiplicative groups in this sense. And here's A4. But anyway, the point is every non-identity element generates the group. It's no accident that this group had prime order, all right? This one, on the other hand, will not be like that. G equals Z25, that's a prime power order, right? Z5 squared. And everything in here is relatively prime to 25, except for what? Multiples of 5. You got your 0, your 5, your 10, your 15, your 20. None of these are relatively prime, so they will not serve as generators to Z25 by the corollary we just looked at, right? In fact, these go into this subgroup. 0, 5, 10, 15, 20. Now, this subgroup is generated how? Additively, right? So instead of looking at powers, we look at multiples, right? Repeated additions rather than repeated multiplications. So the subgroup generated by 5, 0, 5, 10, 15, 20. Before I zoom down here, guys, what else will generate this besides 5? Why? Why? Why any of them besides 0? What's your reasoning? You just can see it calculationally. I think that's possible here because it's pretty small. But the way I'd like you to think about it is that every multiple here except for 0 is a multiple either by 1, by 2. Hey, shut up. Who set my alarm? That was to remind me to start using the projector if I hadn't made sufficient progress. I decided to cut and run earlier. So, anyway, I mean, you guys should see me work out theorems step by step to a certain extent, right? But we can't do that for every theorem in here, otherwise we won't get to the good stuff. Anyway, I mean, we won't. No, we already did the good stuff. I don't know what I'm talking about. But anyway, I'd rather have you think of it this way. This is 1 times 5. This is 2 times 5. This is 3 times 5. This is 4 times 5. 2, 3, and 4 are relatively prime to 5. 5 is the order of this subgroup. So we could apply the corollary that says that you can generate the subgroup using any element which has order, a relatively prime multiple in this case of a generator. So it's the additive version of the corollary we looked at. Like I said, so 2 times 5, 3 times 5, 4 times 5. These are also generators for 5 because 2, 3, and 4 are relatively prime to 5. So one of the things you have to think about in here is for something you understand multiplicatively, right? What's the additive analog? We always should be asking that. Because sometimes we have additive examples, sometimes we have multiplicative examples. The theory, I've mostly stated multiplicatively, right? But for everything we can say multiplicatively for a cyclic group, you can also say additively for a cyclic group. And it might catch you off guard how different they look. Here's another example. This is order 8, right, which is 2 cubed. This one's a little bit more exciting. You've got this subgroup of order 4. You got this subgroup of order 2. Here's a subgroup of order 1, right? A cubed, a to the 5th, a to the 7th serves generators for the whole group because 3, 5, and 7 are relatively prime to 8. Now, this subgroup of order 4, what's relatively prime to 4? 1 and 3. That means that a cubed, not a cubed this time. So what's the generator here? The generator of this subgroup is not a, it's a squared. So a squared cubed will serve as generator for this guy by the corollary we just went over. It's a little bit subtle, right? Oh, I don't even have that typed out. So sorry. But there it is. Another generator for, oh, there it is. I do have it typed. Why do I know this? It's because that's a squared cubed, and 3 is relatively prime to the order of the subgroup, which is 4. Okay. Keep in mind, you can apply the cyclic subgroup theorems to subgroups, which are, of course, also groups, right? Z20. Oh, my goodness. U20's got all these guys. I worked out for you guys in a problem session that U20 is not cyclic. In fact, if you work it out, you get, well, I'm sorry. This is not U20 cyclic subgroups. This is actually Z20 cyclic subgroups, right? The evens, the multiples of 4s, the multiples of 5, multiples of 10, and of course the identity subgroup. So, like for this one, this has order 10, right? So 2 is a generator for this. What else is going to be a generator? Relatively prime to 10, we have 3, 7, 9. So 3 times 2, 7 times 2, 9 times 2, also generators for this subgroup. All right? Now it starts to become less obvious, right, Bradley? I mean, like you could just eyeball the one before. Now that would you'd actually had to do a fair amount of calculation to be sure that 6, 14, and 18 are the only other generators of this subgroup. But that's the case. These theorems I've gone over are extremely useful towards ripping apart the structure of a cyclic group. So let's summarize what was the patterns we've seen. Every subgroup of a cyclic group is cyclic. That's everywhere. You maybe not even noticed it, but that's the case. Every subgroup of a cyclic group is cyclic. Also, something you might have noticed, the order of a subgroup must divide the order of a group. This is true for cyclic groups. It also actually happens to be true in general for finite groups. We'll prove that after test 1, okay? For each divisor of the order of the group, there is just one subgroup with that order. This guy is special to cyclic groups. That's not true for non-cyclic groups. We've in fact already seen that in like some examples. I think U20 is an example. There you have more than one cyclic subgroup of order 2, right? So this is the fundamental theorem of cyclic groups, just what I said. If H is a subgroup of G, H is cyclic. If the order of G is N and H is a subgroup of G, and the order of H is equal to K, then K has to divide N. And finally, for a given divisor of the order of the group, there is just one subgroup of that order, and it is generated simply by a to the n over k. It really is that simple. So cyclic subgroups are like really, really nice. Now the proof is given right here. Let me see if we have time. Maybe we have probably 5 minutes. I'll try to talk through it at least. Well, yeah, let me talk through it. So first of all, suppose you have a cyclic group, right? So that means that everything in it is like a to the power k. So since h equals to e is cyclic, right? Because that's a to the 0, and if you think about it, it's cyclic. So I mean, fine, the identity subgroup is cyclic. So let's just suppose we're looking at a subgroup which is not the identity subgroup in what follows to make it more interesting, all right? So if a to the power k is an element of h, then a to the minus k is also an h because a to the minus k serves as the inverse, right? And its subgroup is a group, so it's closed under inverses, so that has to be in there. So it follows that for every power in your subgroup, you have minus the power, right? So what that means then, of course, is you can look at the set of powers possible for the subgroup, the positive powers rather, right? I can look at n in the natural numbers such that it appears as a power for an element in my subgroup. That's non-empty because I'm assuming I don't have the identity subgroup, right? That means there's at least one non-identity element, and hence at least one, by this argument, positive power. Because if there's one positive power, if I pick the negative power, there has to be the corresponding positive power because that serves as the inverse, right? So this is non-empty, all right? Non-empty subset of positive integers. Therefore, by the well-ordering principle, there has to be a smallest element. Remember that? Math 200? Anyway, it's true. Or the WAP, as I affectionately call it. Anyway, so if t in lambda is the smallest element, we suspect that h is in fact generated by that a to the power t. Okay, so then this argument here shows that. The usual division algorithm stuff. Let's see here. So first of all, any power of a to the t is an element of h by the closure of the group operations, right? That gives you that the subgroup generated by t is a subset of h. Conversely, if you pick something in h, by the division algorithm, you can find q and r such that k is equal to qt plus r, with r being between 0 and t, non-inclusive. So a to the k is a to the qt plus r, but that's a to the qt times a to the r, which tells me then that a to the r is equal to this guy. But what does that mean? That means that a to the r is an element of h, because it's a product of things which are in h. Uh-oh. Well, what does that mean? Well, that's very troubling if a to the r is not the identity element, because that would say that it's a smaller, r would be a smaller element than t, which is impossible, right? So therefore r is equal to 0, and what's that tell us? That tells us then that a to the k is equal to a to the qt, which is to say that h is a subset of the subgroup generated by a to the t. Then we have double containment. Just like we did earlier today, we get equality of the sets. Same song and dance. All right, so, and then for point 2, if you have the order of the group is n, and you have a subgroup of order k, by the proof of 1, we know that we can write h as being generated by a to the t. But we also know that if we raise it to the power n, we get e, right? But we proved last class that if you have h to some power equal to e, that means that that power must be, n must divide that power, right? So that implies then that, oh, wait a minute. Oh, it's not that. Oh, yes, it is that. I'm sorry. I'm an idiot. Here it is. So a to the power t to the e, words. A to the power t has a to the t to the n equal to e. By corollary 1.6.14, that says that the order of a to the t divides n, which is to say that k divides n. I'm sorry, I'm gonna stop talking. I'm about to start coughing again. Idiot. I was going to get a peppermint candy, but I forgot before class. But you have a cough drop?
Actually, I have peppermint.
What kind of cough drops we got?
Honey lemon.
I'll take the honey lemon. Sorry, Lorenzo, but
They're a little hard to unwrap.
Well, class is over. No. So part 3 is pretty straightforward. It's just, again, using all the ingredients we have so far. You have a subgroup of order n. You got a positive divisor k. We use the theorem we proved earlier today to show that the order of the subgroup generated by a to the n over k is equal to n divided by the greatest common divisor of n and n over k, which, by the way, is n over k, right? So that gives you k. Consequently, we get a subgroup of order k is generated. This man. So we get. I don't know if I can. Just I'm not sure multitasking really is possible for me. Good enough. Thank you. Okay, so excuse me. Here we go. So we have that this is a subgroup of order k. If you have, that's part of it, right? But then the claim is that it's the unique subgroup of order k, right? So what we do is we pick another one, possibly another one, right? We want to show it, in fact, it's the same one. So by the proof of part 1 again, h is equal to it's generated by a to the t for some t, a divisor of n. And if you look at t is the greatest common divisor of t and n, right? Consequently, k, which is the order of a to the t, it's equal to the order of the a to the GCD of tn by that corollary we had earlier, which is n over that, which is this, and then check it out. So that means t is equal to n over k. We're back where we started again. H is equal to the subgroup generated by a to the n over k. So, all right. Now, I know I hurried a little bit, but trust me, that theorem is no more profound. The steps I just made are really not much harder than the steps I did at the beginning. It's a little bit more subtle, right? There's a well-ordering argument. So you have to construct that set of positive exponents to get started. If you don't think of doing that, it's hard to prove that theorem, right? But once you do that, it's not that bad. So for the remainder of class, I'm going to talk to you about applications of this theorem and how we can solve problems. In other words, I'm giving you advice about some tricks and techniques for your homework, basically, right? So now you're listening. You guys are listening all along. I'm just being facetious. So the group of units, the order of the group of units in Zn, in fact, has a special name. It's called the Euler phi function. So here's a table. I took Galeon's table to 12 and I added a few numbers for kicks. And so, like, the number of relatively prime numbers up to 2 is 1, because 1 is relatively prime to 2, and that's all you got. 8, what's relatively prime to 8? You got 1, 3, 5, 7. Oh, there's 4. Right? How many numbers are relatively prime to 13? 12. Prime or easy? Okay, so I could easily add a large prime here and put one less than it. Those are easy, right? Number of relatively prime numbers to a prime number. Let's see here. 20 had those 8 things. We looked at U20 a little bit ago. There's some patterns you can see here, right? For example, if you look at the Euler phi function of 20, what is it? It's actually the same as Euler phi function of 4 times 5, right? Because 2 times 4 is 8. But this multiplicative pattern doesn't quite work all the time, right? Like phi of 8 is not phi of 2 times phi of 4, right? The phi of 8 is 4. 2 and 4 are 2. 2 is obviously not equal to 4. So it's not always this, but it's sometimes this, right? It would seem that relatively prime divisors might give a multiplicative Euler phi function. I'm leaving it as an open question. I'm just pointing out there are patterns. I'm not saying what they are yet. But anyway, you're like, fine, I'll Google it. Yeah, that's true. I can't stop you. Anyway, so here's the theorem. If we have a cyclic group of order n, D is a positive divisor of n, then Euler phi function of D is the number of elements of order D in G. So the proof of that is just by the fundamental theorem of cyclic groups mostly, right? So G is cyclic with order n, D a positive divisor of n. There's a unique subgroup of order H, subgroup H of order D in G, right? And H has some generator because it's cyclic, right? Every subgroup is cyclic, so there's some generator. And the order of A has to be D because the order of the subgroup matches the order of the element which generates it. And then corollary 17 told us that these guys are equal only if the greatest common divisor of K and the order of this, which is D, right? So D is functioning like N was before in the corollary. But this being 1, well, what is that? That's exactly, how many such K are there? How many relatively prime K's are there to D for a given D? That is phi of D by definition. That's the number of relatively prime things to D. Consequently, the number of distinct choices for K is precisely the Euler phi function of D. Thus, the number of elements of order D is precisely phi of D. Now, what makes this kind of, on first glance, really surprising is that it's true, you know, whether you're looking, for example, n equals 19k, groups like that. So you could look at one hand, you could look at like, you know, Z19, but you could just as well look at Z19 million. The number of elements of order 19 is 18 in this guy or that guy. Because the number of elements being, you know, 18 of, you know, elements of order 19, there being 18 of those is completely governed by the fact that phi of 19 is 18. It doesn't matter whether that's 19 appearing as a divisor in the order of Z19 or 19 appearing as a divisor in the order of Z to the 19 million. That's kind of surprising. You might think that the universe in which you're looking at would determine the number of possible elements of order whatever. That's partially true, right? It has to be connected to the order of the group, right? You can't have an element of order 11 in a group of order 15 because 11 is not a divisor of 15, right? At the moment I'm talking about cyclic groups because that's all we know. There's a little bit more you can say. In a finite group, the number of elements of order D is divisible by phi of D. Now I'm not assuming a cyclic group, just a finite group. So what you do is you just like take your finite group, you pick an element of order D. You look at the subgroup that generates it. How many things are in there? How many elements are in the subgroup generated by A that also have order D? Phi of D, by the theorem up there. So then you pick something else that's not in that subgroup generated by A. And then you look at all the elements generated by B. Again, there's phi of D of those elements which have order D. And there can't be any kind of interlinking between these two things, otherwise it gives you a contradiction. So you just keep getting phi of D worth of elements order D, phi of D worth of elements order D in like disconnected buckets. You add them together, that gives you a multiple of phi of D. For example, in U20, we had elements of order 2. How many of them did we have? Paper. Knew it was going to happen. What's that? I'm trying to remember. Maybe I actually wrote it down in my notes, so I don't have to remember. Well, here's a good example. Here it is, U20. So U20 is this. There are 3 distinct subgroups of order 2 in U20. This alone shows that U20 is not cyclic. In fact, once you find 2 groups of order 2, game over, not cyclic. So if you go back to that help session, I didn't have to calculate all that. If we know the theory that we know today, once you find 2 subgroups of order 2 which are distinct, right? In other words, if you find 2 elements of order 2 which aren't equal, it's not a cyclic group. Now, if you find 3 elements, if you find an element of order 3, if you find 2 which are distinct, I don't think that quite does it, right? Unless what? They need to generate separate things, because you could have that like your in a subgroup of an element of order 3 is going to generate an order 3 subgroup. So that can have 2 generators because phi of 3 is 2. More paper. Excuse me. Anyway, as usual, I'm out of time. But here is a list of things that you could look for as being violations of cyclicity. 2 elements of order 2. 2 elements A not equal to B of order 3 with B not in the subgroup generated by A. More than one element of order D that generate different subgroups. More than one subgroup of a given order. Positive divisor D of G, and yet no subgroup of order D. These are all dead giveaway, not a cyclic group. So where the theorem of cyclic subgroups really gives to you is in proving things are not cyclic subgroups. Anyway, I shut up. Thanks, guys.